Okay, now let's talk how to do these things in R. And the first thing we need to learn is factor. Factor is a special variable in R, which can be used for qualitative variables. So every time you have a qualitative variable, it's a good idea to make it as a. Let me show you an example. Let's say we have a variable g, which some levels, for example, it can be 1, 1, 1, meaning the first group, and then 2, 2, 2, meaning the second. So if you show the variable g, we will see this just as a numeric variable. So if you look at this one, you can see it's just a numeric variable. Now you can make it as a factor. If you use a function factor, so you can see, for example, g is a factor. Let me use another variable. g1 is a factor, and then you use g to make it as a. Okay, so if you show the g1, you see a very small difference. You also see the values, and then you see levels 1 and 2. Okay. Then if you look at the global environment, you can see it's not a numeric variable anymore. It's a factor with 2 levels, 1 and 2. So it tells R this is something for making groups. So now R can use this variable for creating groups, for creating subsets of. You can also make a factor with some level names, the text number, the text labels. For example, G2 is a factor, G, and then you give a label, a text label for every level. For example, in this case, we have 2 levels. So we say labels. Then we need to add 2 names. For example, let's use rain and sun. Then show G2. So look, now we have rain, 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 and sun, sun, sun. Even though if you look at the global environment, you can see inside this variable you have numbers 1, 1, 1, and 2, 2, 2. But because R knows it's a factor, it has these labels for the levels, so it understands that if it's 1, it's rain. If it's 2, it's sun. So it uses this when it shows or when it does all calculations. It uses the label. Okay, so this is how to make factor. Very often when you read data using read CSV or read Excel, if you have a column with text values and if the amount of values is limited, R automatically assumes that it is a factor. Okay, let's see that. Well, let's take I prepared 3 data sets, apples 1, apples 2, apples 3. These are data sets that corresponds to the examples I used for the pen casting. Okay, so let's start with apples 1. We will use ANOVA 1 with apples 1. So let me get the data. Say read CSV. I will use CSV2 because in this case I use the Danish regional standards. And then it's apples. Then I will show the data. In this case I don't have a matrix. I have a data frame with 2 columns. The first column tells me from which tree the values came. So this, you see the same 10, 11, 12, 13, 14 for A, then for B, and then for C. Okay, the order may be different. The values are the same. And then if you look at the data frame, you can see that 3 is already factor, so you don't have to make it as a factor. It's already a factor. But it's always a good idea to check that this is correct. So in our case, sugar is our values. It's in this case, it's integer. And then 3 is a factor, so we can do ANOVA. Now I'll show you how to make ANOVA model. So M1, model 1. So it's AOV function. It's called AOV, analysis of variance. And then you use this formula, the relationship, right? So you say, I would like to relate sugar and the tree. Okay, sugar related to the tree. And then you just add where the data came from. So data is D. So it means that take these 2 columns, sugar and tree, from the data frame. And then we make a summary for the whole model. Now let's run it and look at the summary. So this is the summary. Look, these are values. They correspond. If you look at the video, you will see that we got absolutely the same value. So this is degrees of freedom. We have 2 degrees of freedom because it's 3 groups. And we have 12 degrees of freedom for the residuals because we lost 1 when we calculate average, and we lost 2 degrees of freedom when we compare the. Now this is a sum of squared values, 10 and 30. And these are the mean squares or the variances, the 5 and 2.5. This is F value, and this is the probability to get F value like we have, or even more extreme, if indeed there is no difference. And you can see indeed it's 18%. I'll show you quickly how the F distribution looks like in this case. So if we generate, for example, F values as a sequence between, let's say, 0 and 10, then let's generate like 200. Then we can calculate the density for every for every f value using the Fisher distribution, the density function for the Fisher distribution. And it's 2 and 12 degrees of freedom. Remember, 2 and 12 degrees. Then we can make a plot. I will change this because f is used for false, so I will change this like fv, f value. Then we can make a float. F value and the density type equal to L. And then I will make it. So if you run this, we will see the distribution. So this is how the distribution looks like. So you see that most of the time we will have somewhere between 0 and 2, and then 4 is extreme, getting extreme more and more. And 8 will be very. So we have 2, so this is 2. So our p-value will be all the area to the right part of the 2, because this is where we have the extremes. And you can see that the area is indeed, it's relatively low. The p-value of the area is 0. Now, what if we take the other case, right? So, where the variation of sugar inside each sample is smaller, okay? So I take a data set, I will use the same variable. Read CSV. It's apples 2, I call it apples 2. And just making another. I'll show you. You remember that we now we have a smaller variation of the values inside each sample, so it's 11, 11.5, 12, 12. So the range is twice small ranges. So let's see if we get the same result as in the pen casting. So we make another model, another model, so sugar, the same model, sugar related to trees, sugar related to tree, and then the data equal to. So if you look at the summary, we'll see some interesting things. First of all, the summary looks a little bit different. So now you got, the table is the same, but now you have these 2 asterisks here, and then you have some strange legend here. So let me explain that. Well, first of all, the values are the same. We have 2 degrees of freedom and 12 here. We have, this is a sum of squares. These are the average squares, so it's variance. It's 5 and then the f value, it's 8. It's 8, okay? Then you can see that it's quite extreme because the distribution is the same. The number of groups and number of values is the same. So the p-value is 0.062, so it's less than 1%. When p-value becomes very small, R shows you this significance code. Okay, the more asterisks you have, the smaller p-value is. For example, if p-value is between 0.1 and 1, you see nothing, like we did it. If p-value is between 0.05 and 0.1, it's dot. It just makes you a warning. It seems like p-value gets too small. Then it's between 0.01 and 0.05, it's a star. So it means that it seems like it's less than 5%. Okay. Then if it's less than 1%, you have 2 stars like we have in our. And if it's less than 0.1%, you have 3 stars. It's just, especially for beginners, it helps you to see how small the p-value is, how extreme you set. That's how to do ANOVA 1. Now let's talk about ANOVA 2. And again, I will use the same example as in the pen casting, where we compare trees and the weather. So I get the data. It's apples 3. It's called apples 3. And they show the data. So these are the values. Again, I use this table representation because that's how ANOVA in R works with. So you need separate columns for groups and the values. Okay, so we have sugar, and then we have 2 factors now, tree and weather. Let's check if indeed it's a factor. So if you look at this one, you can see tree is a factor with 3 levels, weather is a factor with 2 levels, and then sugar is. Okay, so everything seems to be okay. Now let's make ANOVA. We use the same function, AOV. But in this case, the formula will be following. You say sugar related to, and then you need to say it's a combination of the 2 factors. Tree plus weather. And then the same data equal. Now let's look at the summary. So again, if you look, now you have 2 rows and then the residuals, because we have two different factors, right? So remember, for the trees, we have also 2 degrees of freedom. This is our sum of squared values. This is the variance. And this is the f value and the corresponding. So you can see it's 0.8, and 2 stars means that it's less than 1%. For the weather, you have 1 degree of freedom. The sum of squared values is 72. Again, check them. We got the same when we did this pen cut. Then that's the f value, and that's the probability to get a sample like we have, or even worse, if there is no difference if weather doesn't influence the sugar. And then you can see it's 3 stars, so it's a very highly significant statistician score. So it means that it's less than 0. Again, and then you have this residual. Now let me show you what happens if we forget to take into account the weather, okay? So say, let's take into account only trees. Let's call it 4. So you can see that now we don't see any difference. Why? Because the residual is huge. Look at the variance for the residuals. It's 5.6, and the F value is small. Why? Because we didn't specify the weather as a separate factor, it just took these two together. So it will be 17 plus 12 divided to 15. 17 plus 12, it's 84, and if you divide it to 15, you will get 5. So if we do not specify all sources of systematic variation, these sources will go to residuals, and therefore very often you will not see an effect even though the effect is present, like we did it. And then finally, now let me show you how Toki works. How to make Toki test. Then let's start with the second model where we have only trees, and then we saw a difference. I will call it T1 Toki results. So you say Toki HSD, and then just provide the model. So you don't need to provide the values, only the model. So for example, let's start with M1. Then you can show the results, or you can plot the result, or you can do both, of course. So let's start with showing the results. So these are all possible combinations for the trees. So you can see that it tells you that it's Toki test for multiple comparisons of means. That's the confidence level. This is the formula you use to make an ANOVA model. And then this is the tree. So for example, if you compare B and A, this is the difference you've seen. This is the possible difference. It's a confidence interval. And you can see it crosses 0. This is the p-value. So in none of the cases we see any difference. Then if we plot this, so this is the plot, you can see that all 3 confidence intervals actually cross 0. So we don't see it. But if we make the Toki test for the second model, M2, then show the results and plot the results. So now we see a difference, right? But you remember that we understand that at least one group is different, but which one? Okay, let's see. B and A, no difference. C and B, no difference. But C and A, you remember that was the biggest difference. We see a difference. Okay, the p-value is quite small, so there is an effect. How big the effect is? Well, C is smaller because we have negative. The average sugar content in C is smaller than in A. How big the difference? Between 0.7 and 3.3. In this case, it's percent of total mass. Okay, so somewhere in between with 95%. So now you can see how big the difference is. And then if you make a plot, you can see that indeed these 2 confidence intervals cross 0, but this one is not. Okay, so the difference, maybe it's not very big, but still you see it. So you can use the confidence intervals to find out how big the. Now, if you use Toki test for two-way ANOVA, then there is a small difference. So you have to specify both models, and then you have to specify the name of the factor you want to investigate. Okay. If you don't specify that, then it will show all factors. But if you specify that, it will show only one particular factor. It's up to you which way to use. I always specify the name. So for example, if you specify tree, then show and plot the results. So you can see that now it's a trees. It's not M3, of course, it should be. I have to run like this. And now it's so this is the let me show you. So this is the comparison. You can see that again, we don't see a clear difference between B and A, and we don't see any difference between C and B. The p-values are quite large, but we see a clear difference between C and A. Okay, and in this case, you see that the difference is between 0.6 and 3.4% of total. And then if you plot it, you will get almost the same. The only difference is that I mixed the trees and this. Also the A and B and C, they have a different. So we don't see a difference here, but here we have a difference. Not very big, but still. And then if we do the same for the second parameter for the weather, you remember in weather we have only one group, so we have only one pair. Just use a T4. We have to use the same model. So for the weather, of course, you see a clear difference. You see the p-value is very small, and the difference is between 3 and 5. Okay, so if you use the reality was 4 in our case, but so if you pick up apples in sunny day instead of rainy day, you may expect the difference in sugar content between 3 and 5. Between 3 and 5 is 95%. So that's the plot. You don't see any zero values here because it's far from zeros. Okay, but you can of course add this xlim equal to c, for example, 0 and -1, 4, and now you will be able to see how far your confidence interval from the let's use not 4 but so now you can see how far your confidence interval from 0, right? So you can see that the effect is really pretty high, pretty large. So that's how to use ANOVA and Toka's test, and for the Bonferroni correction you just need to correct alpha manually.